Okay, this lecture is about subgroups, but before we start, I was just uploading the last video and I noticed on my YouTube stats that somebody has smashed that like button, so thank you to you. Anyway, when we defined vector spaces, when we discussed in this course vector spaces, we introduced the idea of a subspace of a vector space. And a subspace was a vector space sitting inside another vector space, so it's a subset of another vector space, which was a vector space using the same operations. So we're now going to make the analogous definition for groups, and this definition is called a subgroup. So the idea we're trying to capture is of one group which is a subset of another group and is a group under the same operations, so it uses the same group operations. And here's how we make the definition work. And again, this is very similar to the definition we made for subspaces. So a subset of a group G is called a subgroup if and only if it's got the following three properties. So first of all, it's got to contain the identity. So property 1 says that your subset H must contain the identity element. Property 2, this is sometimes called closure under inverses. So let's just label this closure under inverses. And this says if you've got an element in the subset H, then its inverse has to be in the subset as well. And finally, part 3 says that if you've got two things in H, then their product is also in H, their product under whatever the group operation is. So this is called closure under the group operation, or sometimes just closure. So as usual, there's some special notation for saying that H is a subgroup of G. We write H less than or equal to G to mean that H is a subgroup of G. Alright, let's look at some examples and some non-examples for subgroups then. So first of all, we're going to look at the group of integers, and we're going to look at a subgroup of the group of integers. So we're going to define 2z to be all the multiples of 2, so all the integer multiples of 2. So in other words, all the things like -4, -2, 0, 2, 4, and so on. You'll see this notation used commonly, so when people write nz, they mean all the integer multiples of n. So this thing is a subgroup of the group of integers under addition. So I'm just going to write z, but as usual, whenever we talk about the group z, we mean the group operation to be addition. So let's check that this thing really is a subgroup. We have three conditions to check. Point 1 is, does it contain the identity? Yes, it does. The identity in z is 0, and 0 really is in 2z. Okay, so condition 1 is fine. Condition 2 says that if something is in our subset, then its inverse must be in the subset as well. Well, in the integers, the inverse of an integer a is -a. And it is true that if you have an element of 2z, then its inverse minus that is also in 2z. So condition 2, if let's say m is in 2z, then -m is also in 2z too. The elements of 2z are the even integers. If m is even, then so is -m. So we are okay. We've passed condition 2. And condition 3. Condition 3 says that if you have two elements of your would-be subgroup and you combine them using the group operation, then that's still got to be in this would-be subgroup. And that's true for us. So if I take two elements of 2z, I can write them as 2a and 2b. But if those two things are in 2z, then when you combine them with a group operation, you get 2a plus 2b. And you can see that's again a multiple of 2. That's 2 times a plus b. So this thing is in 2z. So again, we're fine with passed condition 3 as well. So this subset 2z of the group z under addition genuinely is a subgroup because it passed all three conditions. Right. Now let's think about the natural numbers n. So we're going to ask, is n a subgroup of the integers under addition? Okay, pause the video, see if you can figure it out. Okay, I hope you really did pause it. Well, the answer is no. Let's check the conditions one by one. So condition 1, that's fine. The natural numbers do contain 0, at least with our definition of the natural numbers. They do contain 0, and 0 is the identity element in z. So condition 1 is fine. Condition 3 is fine as well. If you add two natural numbers, you get another natural number. So condition 3 is fine. But condition 2, that is not okay. That is not, does not pass because, for example, 1 is in n, but its inverse minus 1 is not in n. Okay, it doesn't pass condition 2, so it is not a subgroup. Okay, let's look at a more interesting example of a subgroup. So we're going to take an, this is going to be a subset of the symmetric group Sn. So this is going to be all even permutations in the symmetric group Sn. So if you can't remember what even means, go and look it up. It means a permutation is called even if you can express it as a product of an even number of transpositions. So then An is a subgroup of Sn. Let's check the conditions. So first of all, condition 1, we have to show the identity is even. So the identity, well, to show it's even, you have to express it as an even number of transpositions. So you could write the identity, for example, as 1, 2 times 1, 2. That is even. So the identity element of Sn is in An. Okay, condition 2. We proved actually during the part of the course on permutations that if you have a permutation S, then S and S inverse have the same parity. Right? Either they're both even or they're both odd. You should go and look up the proof if you can't remember how it worked. So if S is even, S inverse is even too. So condition 2 is okay. If you've got an element of An, then its inverse is also even, so it's also an element of An. And finally, number 3, again, a product of two even permutations is even. We proved this when we studied permutations. So if S and T are even, then their composition, their product under the group operation, St, is even. So what that says is if you've got two elements of An, then their product under our group operation is also in An. It tells you An is closed under multiplication, closed under the group operation, so we've passed condition 3. Okay, all three parts of the definition of a subgroup passed, so An really is a subgroup of Sn. So there is a special name for AN. So AN is called the alternating group. Let's look at a quick example. So, what would A2 look like? Well, A2, the only even permutation in S2 is the identity. So A2 is actually, it's a version of the trivial group. On the other hand, if we take A3, and then things get slightly more interesting. This is all the even permutations in S3. So this time we get the identity. We don't get any of the 2 cycles, but we do get both 3 cycles. You will remember that an M cycle is even if and only if M is odd. So the even cycles are the cycles which have length, a length which is odd. So here in S3, the only even permutations are the identity together with those 3 cycles. Okay, if you want to see some more examples of subgroups, you should look at section 4.5 in the online notes. Right, let's move on to a special kind of subgroup, which I trailed in the last lecture, which is what's called a cyclic subgroup. So we're going to take G, capital G, to be some group, and little g to be an element of this group. And then we define pointy brackets G, like this. Oops, let's do this a little bit better. We define pointy brackets G to be the cyclic subgroup generated by G, and we define it to be the set of all powers of this element G. So the set G to the n for any integer n, positive or negative. So this thing's called the cyclic subgroup generated by G, and in order for that name to make sense, we have some work to do. It better actually be a subgroup. So here is our lemma in which we're going to verify that. The lemma says that this thing that I've called the cyclic subgroup generated by G genuinely is a subgroup of G. And furthermore, you can actually say what its order is. If this element little g has order n, then the order of that cyclic subgroup, so the size of the cyclic subgroup, is actually equal to the order of this element. Okay. So this proof then, which we're now going to do, has 2 parts. The first part is we've got to show that the cyclic subgroup generated by G really is a subgroup. The next part, we've got to show it really does have the order I said it did. So to show it's a subgroup, we have to check all 3 of the subgroup tests, all 3 of the parts of the definition of a subgroup. So part 1 was, does it contain the identity? So the identity is equal to g to the 0. That's the definition of g to the 0. And the pointy brackets G, this cyclic subgroup, was the set of all powers. So this thing really is in G. So we've passed the first subgroup test. Okay, part 2. Part 2 was closure under inverses. Well, if you have an element of this cyclic subgroup, it looks like some integer power of the element G. So if you have this power here, well, what's G to the A to the minus 1? It is G to the minus A. You can check that. If you multiply G to the A by G to the minus A, what you get is G to the 0 by the exponent laws, and that's the identity. So that's telling you that G to the minus A is the inverse of G to the A. But G to the minus A, well, that's just another power of G. So this thing is in this cyclic subgroup again. So we've shown that if you have any element of the cyclic subgroup, then its inverse is also in the cyclic subgroup. So the cyclic subgroup is closed under inverses, it passed condition 2. Okay, finally, part 3 of the definition of subgroup was closure under products, under multiplication. So to check part 3, we have to pick 2 elements of the cyclic subgroup, multiply them together and show that they're still in that cyclic subgroup. But this is easy because we've got the exponent laws. So just take any two elements. They look like g to the a and g to the b for some integers a and b. And then if I multiply them together, g to the a times g to the b under our group operation is g to the a plus b by the exponent laws, and that is in this cyclic subgroup because the cyclic subgroup is the set of all powers. Okay, we've passed all three subgroup tests, so what we have is genuinely a subgroup, and it makes sense to actually call this thing the cyclic subgroup because it really is a subgroup. Okay, so the next part of the proof is to show that the size of this cyclic subgroup equals the order of the element little g. So when the order is infinity, when g has infinite order, this is clear. All of the elements g, g squared, g cubed, and so on are distinct. So you've got infinitely many things inside the cyclic subgroup, so of course it has infinite order. So the interesting case, the case where we've really got a problem, is when g has finite order, so when this n is actually an ordinary finite number. So in order to do this, we will show that every element of the cyclic subgroup pointy brackets g equals one of the identity or g squared and so on up to g to the n minus 1. Once we've done that, we're finished because you know that all of these elements are distinct. We proved that in our last lecture. So if we can show that every element of g equals one of these n elements, and we know that these n elements are all different, then we'll have shown that the size of the cyclic subgroup really is equal to n. So let's do it. If we take any element of this cyclic subgroup, well, it equals some integer power of this thing g. So looks like g to the a for some integer a. Maybe a is positive, maybe a is negative, maybe a is 10 million. In any case, I have to show that it equals one of these powers here, so the powers of g where the exponent is less than the order n. Okay, well, what can I do with my integer n? So a is in z, so I can divide a by n. When you divide a by n, you can write it as a quotient and remainder. We can write a, so whether it's positive, whether it's negative, 0, whatever, we can write it as a multiple of n plus a remainder, where the remainder is between r and n. Okay, now let's look at g to the a. That is the same as g to the, I'm going to write it as n times q plus r. Okay, that's supposed to be a g here. Let's use our exponent rules. That's g to the n q times g to the r. Okay, I'm going to use my exponent rules again. That's g to the n to the q times g to the r. But n was the order of g, so g to the n is the identity. So what you've got here is the identity to the power q times g to the r. But if you multiply the identity by itself, you get the identity. That's the definition of the identity. And if you take the inverse of the identity, again, that's the identity. So e to the power q, whatever q is, e to the power q is just the identity again. So we have just here g to the r. Now look at what r was. It was some number between 0 and n. In other words, g to the r is one of the things on my list here. So this arbitrary element, g to the a of our cyclic group, actually equals g to the r, which is one of the things on this list here. So we have done. Okay, we've completed our lemma. Alright, so what came out of this proof then was actually that if the order
If little g is equal to n, then we have a nice expression for our cyclic subgroup. The cyclic subgroup generated by G, we can actually just write it as the set E, G, G squared, and so on, up to G to the n minus 1. And those things are in fact all different. Okay, so there's our lemma about sizes of cyclic subgroups. Let's move on to our last slide. We're going to look at some examples of cyclic subgroups. So first example then, let's revisit a subgroup that we've already seen. So if we look at 2z, remember that was the set of all multiples of 2, all integer multiples of 2. We showed that was a subgroup of the group of integers under addition, but in fact is a cyclic subgroup. So 2z is the cyclic subgroup generated by 2. And the reason for that is the cyclic subgroup is the set of all cyclic subgroup generated by an element G is the set of all powers of G. Powers means what can you get by combining your element with itself using the group operation, and what can you get by combining the inverse by itself with itself using the group operation. So here if you combine 2 with itself using our group operation, which is addition, then you get 2, 4, 6, 8 and so on, so the positive half of 2z. And if you combine the inverse of 2, so that's minus 2, with itself using the group operation, you get minus 2, minus 4 and so on. So the set of all powers of 2, according to our definition, really is this set 2z. So we have that this subgroup is actually the cyclic subgroup generated by 2, but what's more, it's also the cyclic subgroup generated by minus 2. So you should think about why that's the case. Alright, there's an example. Let's look at another example of a cyclic subgroup. So let's look this time inside the symmetric group S4. So if we look at the cyclic subgroup generated by 1, 2, 3, 4. Okay, that element is a 4 cycle. So it's got order 4. So I can write down straight away, without doing any calculations, I can write down exactly which things are in this cyclic subgroup. It should be the identity, then the first power, then the second power, then the third power, and that's it. We get to stop there, one less than the order, which was 4, so we can stop there. Okay, so that is exactly this cyclic subgroup. It consists of these 4 things because the element whose cyclic subgroup we were looking at has got order 4. So this thing is equal to E, 1, 2, 3, 4. If you do this, you get 1, 3, 2, 4. Check that permutation multiplication. And lastly, you get 1, 4, 2. No, you don't. You get 1, 4, 3, 2, the inverse. Okay, so there is a cyclic subgroup generated by 1, 2, 3, 4. This is actually, if you look at the cyclic subgroup generated by 1, 4, 3, 2, you get the same thing, but it wouldn't be the same as the cyclic subgroup generated by 1, 4, 1, 3, 2, 4. Okay, pause the video, work out what the cyclic subgroup generated by 1, 3, 2, 4 actually looks like. Okay, I hope you really did it. 1, 3, 2, 4, this double 2 cycle, double transposition, has got order 2, so the cyclic subgroup it generates should have order 2. So this thing is actually just equal to the identity. I've been writing this as ID or E, doesn't really matter, and 1, 3, 2, 4, and that is all. That's the only thing which is in that cyclic subgroup. Okay, last example then. Let's look at one of the groups of integers mod n. Let's look inside the integers modulo 6. We're going to look at the subgroup generated by 2 inside the integers modulo 6 under addition. So if we want to know what's in there, well, the easiest thing to do would be to work out the order of 2. So it's not got order 1 because it's not the identity, which is the class of 0. It's not got order 2 because if you look at 2 plus 2, you get the class of 4, which is not the class of 0. But if you look at class of 2 plus class of 2 plus class of 2, you get class of 6, which is the class of 0. It is the identity in this group. So the order of the class of 2 is 3. So now I can write down straight away what are the elements of the cyclic subgroup of Z6 generated by 2. And the answer would be, you just get the first 3 powers. You get the identity, which is the class of 0, the first power, which is the class of 2, and the next power, which is the class of 4, and that's all. Alright, so inside Z6, this is what the subgroup of generated by 2, the cyclic subgroup generated by 2 would look like. On the other hand, if you work, so actually let's have one more example, just to make the point that it really matters which of, whether you're working in the integers mod 6 or in the integers mod 4, in the integers mod 8, whatever. So in Z4, you should check that the class of 2, so I'm going to write subscript 4s here to remind ourselves that now we're working modulo 4, this has order 2, not 3, so this time the cyclic subgroup of the integers mod 4 generated by 2 would just be the identity, that's the class of 0, and class of 2. Okay, let's stop.